Hello, my name is Rhonda Aiken, and today I will be exploring the multiprocessor scheduling problem, SMP, a fascinating NP hard problem with broad applications in modern computing and operations research. The problem, which is for this multiprocessor scheduling program, arises when we need to assign tasks to multiple processors while minimizing the make space, which means the total time to complete all tasks. Tasks can be represented as a direct acyclic graphic, or DAG. They use nodes, or verticals, which represents the task. And then we have the edges, which represents dependencies, indicating that one task must finish before another starts. So you ask why MSP matters. Well, efficiency scheduling is critical in areas such as industrial project management scheduling tasks for assembly lines, cloud computing, optimizing task allocations to virtual machines, and distributed systems, which this is coordinating workloads across servers. So the complexity of MSP is NP hard, meaning finding an optimal solution in polynomial time is infeasible. This problem is computationally expensive as the number of tasks and processors grow. So, how is this applied to the real world? So, where's the real world challenge here? Imagine scheduling thousands of tasks with interdependencies across dozens of processors in a server farm. Metaheuristic algorithms are used to find approximate solutions efficiently. So there are some key characteristics of our NP problem. The first one is verification in polynomial time. So while finding a solution is difficult, verifying one is computationally feasible. Number two is this non-determinism, which in theory, a non-deterministic Turing machine could explore all possible solutions simultaneously. The metaheuristic techniques for multi-processing solution scheduling problem, the metaheuristic provide a practical ways to address MSP when exact solutions are computationally prohibited. So, what are metaheuristics? Well, they're a high level frameworks for optimization. They work well for problems with large, complex search spaces. They aim to find good enough solutions with reasonable time. So, what could be some of the advantages of this? One is flexibility. It's applicable to various domains. Two, which is really important, is scalability. It can handle large problem instances, and its efficiency. It focuses on near optimal solutions. So I have 6 examples of metaheuristic techniques. The first one is the genetic algorithms, GA. This is inspired by natural evolution. The process selection, so this retains the best solution. It does a crossover, which combine parts of solutions. And then mutation, it introduces random changes. So, an example of this could be assigning tasks to a processor by evolving task assignments over generations. Its strength, it handles constraints and adapts well to complex problems. Number two is the simulated annealing, SA. This mimics metal cooling to avoid local optima. It gradually reduces the probability of accepting worse solutions over time. If we to apply this to an application, it's optimizing task assignments by cooling the solution space. The third example here is the ant colony optimization, ACO. This is inspired by ant behavior. So the pheromone trails guides ants towards optimal paths. Solutions are reinforced over iterations. An example in MSP, ants iteratively improve tasks to processor assignments. Number four is the particle optimization, PSO. This models solutions as particles in search space. Particles adjust positions based on personal and collective experiences. The application for this is assigning tasks efficiently by simulating processor swarming. The fifth one is taboo search. This maintains a taboo list to avoid revisiting poor solutions. So it basically, if there was a poor solution, it's going not to go back to it. It refines promising solutions iteratively. And then the sixth one is the mimic algorithm. This combines the genetic algorithms with local search techniques. Its strength is it balances global exploration with fine-tuned optimization. So, how is these applications and real-world cases? So, meta-heuristic algorithms solve real-world MSP challenges. The first one is the cloud computing. This allocates tasks to server data centers. A second one is manufacturing. This is scheduling assembly lines to minimize downtime. And then a third application could be project management, which it's coordinating interdependent tasks across teams. And I provided some visuals here. This is the first one. So this is a conceptual visualization of the multiprocessor scheduling problem. This image illustrates tasks represented as blocks distributed across multiprocessors, which are the horizontal lines, with dependencies between tasks shown using arrows. It visually demonstrates how tasks are assigned to minimize make space efficiently. This style of representation is ideal for teaching or explaining scheduling algorithms and solutions. This next visual, this is a visualization of the multiprocessor scheduling problem. The diagram uses a NAT chart format, illustrating tasks as colorful blocks assigned to 4 processors with clear labels for processors. We have P1, P2, and time increments with them. The dependency between tasks are indicated with arrows. highlighting task relationships and scheduling strategies to minimize the overall span. The third visual I have here is this is an illustration combining the objective formula for minimizing the make space in the microprocessor scheduling problem with visual aids like timelines and task dependencies. The formula reflects the maximum completion time across all processors, and the graphical elements provide clarity for technical purposes. And then the quantum algorithms for MSP. So, quantum inspired approaches leverage principles of quantum mechanics to optimize MSP. Some key techniques here are the quantum genetic algorithms, which use quantum bits for task representation, outperform classical methods in complex scheduling scenarios. And then number two, the quantum inspired swarm algorithm. This is a hybrid swarm optimization method using quantum superpositions. Its efficiency for minimizing make space. What could be a future potential? Quantum computing has the potential to revolutionize scheduling optimization by exploring exponentially large solution spaces in parallel. So, what are the challenges in solving this MSP? First is search space explosion. The number of possible task assignments grows exponentially with the number of tasks and processors. Number two, dependency constraints. Managing task dependencies increases complexity. And then number three is trade offs. Balancing solution quality with computational time is critical. So, in conclusion, the multiprocessor scheduling problem is a foundational challenge in computer science and operation research. Its NP hard nature makes it a perfect candidate for innovation approaches like metaheuristics and quantum inspired algorithms. Some takeaways here is the metaheuristic like GAACO and MSO provide practical ways to address MSP challenges. Quantum inspired techniques are emerging as powerful tools for tackling complex optimization problems. As a computational demands grow, developing efficient scheduling algorithms will remain essential for industries like cloud computing, manufacturing, and beyond. So, some final thoughts here. By leveraging these advanced techniques, we can optimize resource allocation in increasingly complex systems, paving the way for efficient and scalable solutions to real world scheduling problems. This is the list of references that I used. And then I would like to thank you for listening to my presentation on multiprocessing scheduling problem, an NP hard problem. Thank you.